Okay, so this is the first online workshop which IIIT Lucknow is organizing in collaboration with Global Challenges Research Fund. Now, this fund is from this organization is from United Kingdom. Now, we received more than 1,200 applications, and we have carefully shortlisted you all, while maintaining an equal gender ratio. In the next 5 days, you will be hearing from professors from different IIITs, NITs, and also from our fellow researchers and organizers of this workshop from University of Essex, United Kingdom. Now, our first speaker is Dr. Ashutosh Mishra, who is the Dean Academics and a Senior Professor at IIIT Lucknow. Dr. Mishra has a diverse research background, and he specializes in machine learning and artificial intelligence. So without delaying this session any further, I would request Dr. Ashutosh to please start the learning session. Sir, to you.
Yeah. Can you guys hear me? Hello, everyone. Can you guys hear me? Hello?
Yes, sir. The audio is clear.
Right. Okay. So once again, good morning, everyone. I'm not sure where everybody is from, but I'm assuming that it's probably daytime. Anyway, so good morning. And as Vishal, okay. So before I get started, a couple of points. I have purposely, I'm going to talk about data, how to get yourself data ready for your machine learning applications. And in the event that you have any questions, please interrupt me and go ahead and ask me. Either you can use the chat window to ask me a question, or you can just unmute yourself and ask me the question verbally, all right? I am going to try and share my screen, and my slides are fairly elementary in the sense that I have tried to keep my talk fairly simple, in the sense that it'll get across to hopefully everybody. If you already have advanced experiences, great. It'll probably serve as a good refresher course. If not, it'll hopefully give you something to walk away with as far as data and its importance with machine learning is concerned, all right? So that said, let's get started. I'm going to go ahead and share my screen now. To share my screen, Vishal.
Yes, sir.
Okay. Advanced. Okay. All right. So I hope you guys can see my screen now. Something seems to be. Yeah, can you see my screen now?
Yes, sir.
Okay, right. So the topic on which I'm going to be talking today is getting data ready for machine learning, right? So what does that mean? What do we mean by that? We all want to deploy. So what are we going to cover on this talk? These are the broad strokes. So we're going to get into a little bit of an introduction point of view that data and learning machines. We're going to talk, I'll introduce you, at least provide a refresher content on what learning machines are. We're going to then talk about sourcing your data. Where do you get your data from? We'll move on to data pre-processing and dimensionality of the data. We'll talk about problems, potential problems with data. And then we'll sort of end this talk with, yeah. Okay, and then we'll probably end this talk with underscoring some salient issues that we have not been able to look at through the main body of the talk, right? So, data and learning machines, right? So what is a learning machine? I mean, it's very pertinent to ask, right? What is a learning machine? So at the end of the day, a learning machine is essentially a mathematical model, right? Now, why do we need this mathematical model? Because we are trying to derive some kind of a complex input and output relationship. And this model is what we are trying to evaluate, right? Now, why do we need these models? Why do we need these overly complex mathematical models? Because sometimes, depending on the nature of the problem we're trying to solve, a simple linear function is not easy to, it's simply not possible. For example, if you have multimodal input data, or a multi-dimensional input data, and you want to perform some kind of a classification or some kind of a pattern recognition, right? These are non-trivial tasks. So if it is a non-trivial task and you want to solve this non-trivial task, trying to derive an underlying mathematical model that will do this for you requires you to perform, step into the domain of machine learning, right? Learning machine, right? And what do you get at the end of a successful attempt? You get a mathematical function that takes your input functions, your input variables, and maps them using its built-in mathematical coefficients or parameters to some output. Now that output could be anything. It could be a verdict, it could be a value, it could be an action, right? So, and remember, as far as we are concerned, for the purpose of this talk, we are assuming that the problem is extremely complex and fundamentally nonlinear, right? So that brings our severity of the problem front and center, right? So why do we call them learning machines? The learning denotes the idea of computing the parameters of this model. Now, my favorite analogy of all time is equating your learning machines to a newborn infant, right? The way a child learns how to speak or ride a bicycle or anything like that, if you look at the process that's involved, it is quite similar to how your learning machines get trained, right? How they develop. And I will keep coming back to this analogy throughout this talk, right? And just one more disclaimer. In this talk, the word data will keep appearing over and over again. Please bear with me and please don't give me some leeway on this, all right? Okay, so why do we need, so if I want to build a new model, if I want to build a nonlinear learning machine, or if I want to train it, what do I need? I need information. That information is just another way of saying I need some data, right? So what is data? Data is nothing but a collection of samples, right? As many samples as you can get, a set of samples is your data set, right? Data, okay. But what is a sample? I mean, these are all sort of quasi non-technical terms, right? So samples, what is a sample? Sample is nothing but a collection of attributes, right? What do I mean by that? A collection of attributes, collection of features. For example, if I want to describe a person, so I can say this is a human being, right? So what is a human being? How do I differentiate one human being from another human being, right? So I will say that, well, this human being is of this height, this weight, he or she, this is the gender, this is the hair length, these are the eye color, this is the eye color, this is the skin color, this is the spacing between his eyes, and so on and so forth. So all of these attributes, these are features, right? So at the end of the day, finally, a data set is essentially a collection of samples, with each sample being represented by a collection of attributes or features, right? So now it turns out that the number of features per sample also determine the dimensionality of the data. I mean, how dimensional your data is, your data set is, right? Now, it could be argued that there is something to be said about having a very high dimensional data, and we'll get into that. But for now, let's put a pin on it. But the one keyword, or the one key point that needs to be kept in mind always is that every single sample in your data set must have the same number of attributes or the same number of features. So that's critical. And what happens if you don't have that? We'll also look at that in the next slides, in the upcoming slides. All right. So if you have any questions, please stop me. Right. Okay. Data is your friend. You know, at the end of the day, information. You know, information is power. Data is your power. It is power. You know, you can slice it as you want it, but data is your friend, right? You don't have to be afraid of data. And as a rule of thumb, the more data you have, the better off you are fundamentally. Why? Because just like the analogy of the infant, learning machines are inherently iterative in nature. Now, what do I mean by that? They learn over multiple training cycles. So every time you try to train something, that's an iteration, right? So there is an iteration of showing the data or feeding that data and asking the machine or the model to adapt its parameters, right? And going back to the analogy of the child, when you try to teach him or her the English alphabet or the alphabet, right? You draw the alphabet and then you say that, all right, this is an A and this is also an A, and then this is also an A, right? So these are all data points, right? And the child, and you do this over a period of time, over a number of cycles, and then you assume that the child will learn, right? So learning machines similarly are iterative in nature, fundamentally iterative in nature. So because they're iterative in nature, the more data they get to see, the better off our chances are of developing a well-trained or a optimal model, right? And consequently, the quality of the trained model that you end up with directly depends on the amount of data you have. Now, I just use the word amount of data, right? So it means that the volume of the data I have at my disposal has a direct correlation to the quality of the learning model that I have going to, or I'll end up with, right? But that's just one side of the coin. That's just one part of the equation. The other part of the equation is the quality of the data, or in other words, the variety of the data. Now, and what do I mean by that? I'll get into this more in detail near the end of the talk, but just to give you a little bit of a peek into this. If I only taught my child, for example, this is the A, right? And my child never gets to see that this is also an A, then chances are that the learning of my child or the child is going to be incomplete. Why? Because as far as the child is concerned or the model is concerned, it has not seen the other variants of from an input data point of view or input point of view that maps to the same output point of view, right? So these are all the same letter, they all correspond to A, right? But if I don't show the different variants of the same letter A, I can't expect realistically my model to be able to recognize, right? So the idea is that your data set, your database or your data set should have very high volume, should have high volume, and yet it also needs to have sufficient variety. Now, we'll get more into this a little later, right? Now, where do you get the data from? Right? Data is invariably generated through two fundamental methods, right? One is through some physical process, right? And you capture the physical process through sensors, transducers, and stuff like that, right? At the end of the day, so there is a physical process that's going on, and you want to model this physical process. So that physical process has a certain input, and it has a certain output. You want to be able to, for example, if you want to develop a virtual sensor, right? So how do we develop virtual sensors? We develop the virtual sensors by taking real physical process and trying to model it so that we can create a virtualized sensor, right? Or virtual model, right? So data can come through a physical process or some computational process. Now, what do I mean by that? Let's go back to the notion of, for example, if I have genomic data, right? So somebody has taken these microarray data sets, right? So has taken our physical process and digitized it. And now somebody else came along and ran some computational process to it and generated another data, which is derived from a physical process data, right? So data typically has two primary origins. One is a physical process, the other is being a computational process, right? Now, as you can imagine, that both these processes have certain costs associated to them, right? So it takes time, it could take money, it could take physical resources, it could take different number of people working together, right? So there is a cost attached to it, which means that not everybody can afford to generate their own data. Ideally, you should be able to, or you should, but not everybody can generate their own data. So what happens? Then we end up going to these curated sites, these sites or these locations, online sources, where data sets are being curated by different companies, right? So you have sources like Kaggle, UCI database, you have Amazon data, and Microsoft has released a lot of data. Google has released a lot of data sets, right? So you have all these machine learning databases, you know, and I use the word reservedly, where they're machine learning databases, right? Available for anybody to use, so researchers and students and scientists. Why? Because they've already invested the money, they've already invested the cost in generating data, and they believe, and it's a very, very good idea, right? That if more can benefit from it, great. Okay. Now, this brings me to and this is particularly directed to my young students who are in this talk today, that I have noticed a very disturbing trend, and that is that students tend to, particularly students, you know, and that's okay from a certain point of view, that they will pick a database, they'll select a data source, and then try to figure out what problem can be solved from it. It's like putting the apple cart in front of the horse, right? So if you are learning machine, if you're trying to learn machine learning, fine, okay. There's a certain justification to that, a particular notion, right? Or that idea. But if you are developing something which has a real-time deployment scenario, it's better to have a very clear idea of the problem you're trying to solve, and then figuring out which particular online data set would be the most suitable for you. Now, how do you evaluate that? We'll get into that again a little later, right? But please stay away, particularly in real-time and practical deployment scenarios, that try not to shoehorn your problem to the data rather than shoehorning the data to the problem, right? Okay. So if you are sorting the data from somebody else or somewhere else, right, there's a very high likelihood that the data set that you get from somebody else or somewhere else may not be an exact fit or a good fit, even a good fit for your problem, right? So we have to remain cognizant that because I am using somebody else's data set, I need to take care about examining what information is contained therein and how can I use this information to solve my problem at this particular moment, right? Okay, so we'll get into that again later. Any questions so far? I'm assuming none. Any questions? Okay, right. Here's another issue. And this is again used to, this might serve as a cautionary word for all of you out there. And that is that, please keep in mind that data from one geographic or a demographic region may not necessarily be a good fit for deployment or training a model that is to be deployed in a different geographic or a demographic environment. So I'll give you an example, right? A couple of examples are, for example, if I am using agricultural data from, let's say, North America, where the salinity and soil conditions are different, right? And the different kinds of crops and different crop yields. And I try to develop a model that does some kind of a crop yield prediction for deployment in, let's say, India, right? Now, up to a certain extent, yes, maybe my input-output relationship could be sort of assumed to be uniform. But please understand that the weather conditions in Midwest, for example, in the US, are significantly different, or the salinity conditions are different. So that particular data set may not necessarily be a good fit for deployment in this country. Similarly, if I have medical data that has strong genetic components, right? So if I have a medical study data that has been performed on, let's say, Caucasians, right? And I want to deploy that particular genomic model or trained model on a human population of different ethnicity, I am going to run into a little bit of problems, right? A little bit of problems. So caution must be exercised, right? Whenever you're sourcing data from somebody else, you should always examine whether this data set will have any local bias, will have any demographic bias, whether it will have any geographic bias, whether it will have any ethnicity bias, so on and so forth, right? So you keep that in mind, right? Right. Okay, so now you've got your data. You have received your data. Now what do? You start looking at, well, you start getting ready with your data, right? So you prepare your data, right? So the first thing you look at is the dimensionality of the data. how many features does the data have or not have? How many features would you like to have? Right now, I had mentioned that higher the volume and higher the features, we say that there is a higher information content. So as the number of features increases, the information content also correspondingly increases. Now, it must be mentioned over here that not all features are alike, right? So some features provide more information as compared to the other features. Now, what do I mean by that? What does that mean? Okay. Remember, our objective is to, we are working in the domain of machine learning, right? So our objective is to perform some kind of a discrimination capability or achieve some kind of a discrimination capability, or we want to be able to perform some classification and so on and so forth, right? We want to take some autonomous decisions and so on and so forth, right? So this ability to discriminate between samples or samples of different classes or different endpoints, right? These are obviously, this information is obviously embedded in these features of each sample, right? Now, some features will have a higher discrimination capability, the others may not, right? So we have to keep that in mind, and we'll talk about how to evaluate the best features, right? Having higher number of features also can lead, so having a higher dimensionality can also lead to the idea to what we call as the curse of dimensionality, right? So I'm hoping at least all of you have at least heard about the curse of dimensionality, right? So the curse of dimensionality is nothing very, I mean, it's serious, but it's not very complex to understand, right? So the curse of dimensionality basically says that the volume of your data grows exponentially with every increase in the dimension of the data, right? So your search space increases exponentially, right? And why is that critical? Why is that important? Because remember, your data needs to be stored, it needs to be processed, and when you have a higher volume of data, your computational time, computational resources, and obviously the cost, and quite possibly the performance of your model will take a hit, right? So it'll take, and it can take a serious hit, right? So it is always a good idea to examine the total number of features that you have and how many do you really need. So how do we evaluate that? We'll get into that a little later, right? Okay. High demand. So I've already mentioned that it can also lower the fit. So how do we evaluate what is a good feature? So one of the metrics that you can use to evaluate whether a feature is a good feature or not, or a good high quality feature or not, is by looking at how much of the variance in the data or in the samples can that particular feature explain or account for, right? I'll another example, right? So to explain that with an example, let's say we are trying to classify, there's a CCTV camera being deployed somewhere, and its video feed is being used to classify between at an airport, and we're trying to figure out whether the person is male, female, or has a certain ethnicity, and so on and so forth, right? Now, let's say that the camera is a high definition camera, and it can even capture the color of the hair color, right? We are able to get the hair color. Now, hair color typically it does not have a lot of variance, right? So broadly speaking, people have hair of how many different colors? Black, gray, blonde, white, maybe that's it. Brown, 5, 6. Now, so if I were to use the hair color as a feature, this hair color has a very low variance, right? So if I were to plot the hair color of the entire population sample, you'll find that it's a very narrow banded plot, right? It's a very narrow band plot. So if I were to use, now, somebody could say that, well, it does provide some pertinent information. Yes, it does. It provides some pertinent information. But is the marginal increase in the information worth the increase in the associated cost and the volume of the data space that I am going to work with? Right? So if you can answer that question, and if yes, go ahead. If not, you can ignore it. That have sufficient variance. And by the way, this is exactly how dimensionality reduction using techniques like PCO, principal component analysis, work. Right? So when you want to reduce the dimensionality of the data, we adopt a technique. For example, one of the most common techniques is principal component analysis. Right? So what it does is it maps the data to a different plane such that it maximizes the variance, right? So a plane in which the maximal variance is observed, that is what we call as the principal component, the first component, and so on, the second component, third component, fifth component, and so on and so forth, right? And when you do this, you end up with a sorted set of vectors which explain how and where each number one, number two, number three. So the sorted features or the transform features explains certain percentage cumulatively, the cumulative percentage of the data population. For example, it could be said that if I had, let's say, 10 features originally, then top 5 features, when transformed, right, explain over 99% of the data. They account for the 99% of the data. Then in that case, I could simply go from 10 to 5 features without any appreciable loss in the information content of the data, original data, right? So this is what I mean by principal component analysis or dimensionality reduction. So now who decides how many features to retain or how many transform features to retain? That's you. That's the data scientist. That's the person who's trying to develop the model. We decide on the number of components to keep based on the resources available to us. How much storage do I have? How much storage do I need? How much can I get away with? How much computation time will I take a hit of if I keep the original features, right? So these are the factors you use to evaluate how much of the data can be explained and by how many components and how many, and consequently, how many you're going to retain. Okay. Now, your data has high dimensionality, which you can take care of by using dimensionality reduction. Your data can also have outliers. Now, outliers are very interesting, right? So what is an outlier? Outliers are samples which are at...
What is this PCA work?
PCA, principal component analysis.
Okay. But what
PCA,
is it?
Principal component analysis, right? So principal component analysis essentially is algorithm, is a method to examine how much of the variance in the data set is explained by individual features, right? And it is performed using eigenvectors. I'm not going to get into that. I'm not going to get into the maths of the PCA technique. There is sufficient literature available. But the idea is that you take your data set and you transform it into a different plane. You project it onto different planes, right? And when you project it onto a different planes, you can see in which particular plane is the variance the maximum, or the spread is maximum. Then you look at in which particular projection it is the second highest, third highest, fourth highest, fifth highest, and so on and so forth. I hope that helps.
Yeah, okay, thanks.
Mm-hmm. Okay. So now what about outliers? Outliers are samples that are, well, at the extreme ends. Now, what do we mean by extreme ends? Remember, samples are a collection of features. So if certain samples have very, very high, certain or all features have very high or very, very low values, these are outliers, right? Now, these very high or very low values, now remember, not all features need to have very extreme values. Even some values, some features of every sample can have extreme values and could be an outlier, right? Now, these extreme values, extremely high, extremely low, they can occur due to multiple reasons, right? So it could be because of noise, it could be because of transmission error, it could be because of sensor error, transducer error, so on and so forth, right? I do want to add one more word, that these extreme values could actually also be real values. However, these outliers present a sort of from a machine learning point of view, these outliers really are essentially a trivial classification task, or trivial. They do not present classification challenge. For example, if I am looking at the student scores and I am trying to develop a model that can take a decision on whether to accept a student or reject a student. If I come across a student who has 100 percentile score, there is no decision, there's no process that needs to be conducted to figure out that the student will get admission. Similarly, if a student has absolutely zero score, I don't need to perform any machine learning. I don't need to perform any quantitative decision. That person gets rejected. So outliers do not necessarily require any thought. I mean, I'm being very bold over here, but outliers do not need to be accounted in your data set. So you need to get rid of them. Now, why do we need to get rid of them?
Remote in the data set. Visualization of high-dimensional curves that are not traditionally possible. So outlier prediction is executed in computed metrics.
I can't hear you very clearly. Is there somebody asking a question? Hello? Hello? May I carry on?
Can I ask a question?
Sure.
Sir, don't you think that outliers can help us to more generalize the machine learning algorithm?
Okay, so to answer that question, you have to ask yourself, is this outlier, is this really an outlier or not? Because remember, outliers are some things, are those extremum, or the extreme values, right? So I do not necessarily believe that outliers will help you. If there really are outliers, that your outliers will help you in your generalization capability of your learning model. What they will do is actually make it much harder for your training to converge. Do you understand what I'm trying to say over here? Okay, let me put it this way.
I guess maybe they will increase the loss function too much. So.
Exactly. Okay, let's take the example of a simple machine learning problem, and that is that I am trying to classify, right, two samples, right, two classes, between two classes. Now, from a mathematical point of view, this problem boils down to the notion of creating a decision boundary, right? Now, decision boundary could be linear, it could be nonlinear, that doesn't matter, it doesn't matter. Okay. Now, let's say I have an outlier. I have two outliers, okay? So what will happen is that as you start iterating and as your weights are being adjusted, or in other words, this nonlinear curve is being created. If those outliers are in your training data set, your algorithm will try to push your decision boundary away from the other class and more towards the class with the outliers. Why? Because for it, those samples are valid samples. When very well you know that they belong to this class and I don't need to worry about this. As a result, what will happen is that your decision boundary may start overstepping the actual meat of the data band or data set, where the error might start increasing. Classification error will start increasing, right? For example, let's look at this way, right? So if the bulk of my data, let's say one class is here, the other class, for example, is here, and then I have two classifiers over here, right? So some samples over here. These are my outliers. So if my original decision boundary without these outliers would have been somewhere like this, because of these outliers, I include them in my training database, might get shifted like this, or might even get shifted like this, or like this. As a result, what happens? My classification error actually starts going up. Okay. Now, I hope that helps. Hello? So silence as yes. Okay. Right now, how do we find out what the outliers are? So how do you evaluate? Now, remember, if you have 50 samples and you can plot them, fine. You can visualize these outliers, right? You can see them. But when you have large data sets, right, really large data sets, particularly multi-dimensional data sets, right? If you have more than 3 dimensions, it's not easy, or it's not traditionally possible to visualize the data, right? If you have very high number of data points, again, you need very high computational resources or display resources to visualize the data, right? So how do you figure out what the outliers are? Right? So one common approach is to reject samples which are, for example, more than 3 standard deviations away on either side of the mean value of the data, right? So you take every sample, you take every feature of all the samples individually, analyze the features, and figure out in which particular sample that particular feature is far away from the mean value. So that's one way of doing this. Essentially, what do I mean by that? So let's say I have any particular feature and I've plotted it, and let's say the features have a sort of Gaussian distribution, right? This is the mean. What I'm going to do is I'm going to reject everything that is beyond this, right? So beyond 3 sigma away from the mean. So if I reject all of that, those are my outliers, right? That's one way of doing this, right? This approach usually is a good idea if your features have a sort of an inherent normal distribution. So if your data is inherently normally distributed, has a certain Gaussian component to it, you can adopt this approach. Hello. I noticed somebody there's a lot of noise coming in. Is there anyone who has a question? Anyway, let's move on. So if your data does not have a strong Gaussian distribution or has a normal distribution, then what do you do? Well, then the other common approach or common method is to use some kind of a thresholding, right? So how do you figure out what the threshold is? What would be a good threshold? Now, this is where the inherent experience of the data scientist or the researcher comes into it, right? So the underlying or the implicit assumption over here is that if you are trying to develop a learning model or learning machine for a particular problem, you are aware of the physical process that you're trying to model, right? So you have a fairly good idea of what are the extremas that you don't need to consider, right? So you can use that prior knowledge to figure out what would be a suitable value threshold. Then we go to data scaling. Now, why is this important? If you could just give me 1 minute. I had mentioned that the data is generated through a physical process, right? So you have the sensors and transducers that are capturing the data, digitizing it.
Data scaling, Max Normalization.
Hello? Hello? Is there a question? Does someone have a question? So your data is your data is really, at the end of the day, is multimodal, right? So it has multidimensional, and each dimension is being generated, or each feature is being generated through a different kind of a transducer, different kind of a sensor, or a different process, right? Which means that it is very likely that for every sample, the scale of the numerical value for each feature may be different. What do I mean by that? For example, again, going back to the idea of classifying or identifying human beings. If we measure the height of somebody and weight of somebody, okay, they might be in the same order of magnitude, right? But if my sensor, for example, if the load cell that I'm using to capture the weight, for example, right, is is giving me an output in, let's say, millimeters, then I am working, my height is coming in a different scale of value, range of values, and my weight is coming in a different range of values. Right? So if your features have different scale of values, then you are going to have some serious problems. What are those problems? Right? The problems are that you have to keep in mind that every single machine learning algorithm that we talk about or we try to deploy or we try to use, at the end of the day, is a mathematical process, right? It is trying to evaluate the parameters of the model through an iterative mechanism, right? So it is a constant learning and adjustment, learning and adjustment process, right? So when you have numerically large values appearing as an input, along with numerically much smaller values, those numerically larger values are going to have a significantly more impact on the way these model parameters are adjusted. Now, to give you an example, if I was trying to develop an artificial neural network, right? So there are weights in this artificial neural network, right? So between input layer, hidden layer, and output layer, right? Now, at the input side, if I have numerically very diverse range of values coming in, then those nodes which have significantly higher range of values or magnitude of values will end up providing a significantly higher input to the hidden layer. Consequently, when I'm adjusting the weights of those links, of those input nodes and those hidden nodes, there will be a stronger bias of those particular weights being adjusted disproportionately compared to the other nodes. Right? So now it is, and this becomes even more critical if these features are not as important as the other low magnitude features. Right? So how do we get around this problem? So the best way to get around this problem is to make sure that every feature is scaled to the same scale. Right? And this is essentially the notion of data scaling. Right? So two of the most common methods are one, min-max normalization, the other is standardization. Right? So when you are using min-max normalization, this is the expression for this. So xi dash is xi minus min x of max divided by the span of the data, right? So max x minus min x, right? So here xi is a feature of the ith sample of the data, right? So when I say min x, I am talking about the minimum value of feature x across all samples. Right? So similarly, may I carry on? Okay. Similarly, we have standardization. Standardization is nothing but xi is xi minus mean of x divided by standard deviation, sigma of x. Right? So what is the difference between these two methods? Min-max normalization will yield values which are between 0 and 1.
Hello.
Only 0 and 1, right?
Yes, yes.
Standardization, on the other hand, will give you values which have 0 mean and a unit standard deviation. In other words, min-max normalization does not change the shape of your data, while standardization can potentially change the shape of your data, right? Because your original data may have a higher variance, but when you do a standardization, that variance becomes 1, right? So unit standard deviation, right? So so how do you decide which method to use? Well, this is sort of a multi-dimensional answer to this question, right? So you take a decision on the scaling algorithm to use depending on what is the, depending on what sort of machine learning algorithm you're using, what sort of hidden functions or non-linearities you're using in that function, and so on and so forth. And I'll touch that as well a little later, right? So we've talked about data scaling. Now, what about other data pre-processing, right? So you talked about data labels. Now, what are data labels? Now, data labels are essentially what we call as the target values. Now, this is pertinent and very, very critical when you're talking about supervised learning. Now, what is supervised learning? Supervised learning in a nutshell is explained by the following line. You present the data to the machine, to the algorithm, and you tell it what this data is. In other words, if going back to my example, if I draw this, so I am showing this to the child, and I am saying that this is the letter A, right? So I tell the child that this is letter A, right? So this is the data label, right? So in this particular case, my data label is non-numeric, but at the end of the day, you will have to sort of encode your data to a numerical value, right? Some form of numerical value. Because why do we need a numerical encoding for the data label, data targets? These are also known as target values, right? Why do we need a numerical encoding? Because the quality of your training is measured by the amount of error that is obtained in each training cycle. Now, how do you measure the error? Error is nothing but the difference between the target value and your current output value, right? So if my child is going, if I show him this and I say that this is, what is this? And it says, ow. So he's not, there's a significant amount of error. Next day, if I show him the same alphabet and say, what is this? He says, I. So he's getting there, right? So the error is reducing, right? That's the idea. So your target values are going to be numeric, right? Okay. So if my target values are going to be numeric, and I need to figure out what will be a good numeric scheme to perform my data encoding or label encoding, right? So here is something really important to keep in mind. If your network under training employs a non-linearity that saturates at value k, then your target value, any target value greater than k would yield a perpetual error, preventing the convergence of training and leading to a poorly trained model. Now, what do I mean by that? So to really explain this, here is what I'm going to do. I'm going to take the example of an artificial neural network, right? So if you remember from artificial neural networks, you have all these hidden layers, and then you have these output layers, and you have these interconnected weights, right? And so on and so forth. And you have, at each of these nodes, there sits a function. Now these functions are called what we call as a squashing function or a nonlinearity, right? And these functions are the reason why neural networks have such expressive capability, right? Now, one of the most commonly used squashing functions is this sigmoid. Now this function sits here, it sits here, it sits here. Now this is your output value, right? Now if you are using a sigmoid function at the output node or output layer, so if you notice carefully, this sigmoid function has an output between 0 and 1. The output value can vary from 0 and 1 depending on the input value, right? Whatever the input value is, the output cannot exceed the value of 1. And it cannot go below 0, right? Now, if your data encoding is such that your labels are encoded with values greater than 1, say 2, 1.5, 3, whatever, then it stands to reason that that particular node will never be able to converge or achieve a 0 error, ever. So when you're measuring the performance, the training performance per iteration, you will never achieve convergence, right? Now, so the point I'm trying to make here is that your data encoding or your label encoding precisely needs to be network architecture aware. The encoding needs to be cognizant about the network limitations or your architecture limitations, right? Similarly, if I were to look at another non-linearity called the hyperbolic tan or tan H, right? So it also saturates at between 1, but in this case, it goes up to -1. So any output value outside this envelope will never be achieved. You'll never get it. So you'll always have a perpetual error. Nowadays, a very commonly used nonlinearity or the activating function is called rectified linear units or ReLU. So the advantage over here is that for all positive values, you have a linear output, and that linear output is unconstrained, right? So it can go to whatever numerical value you want. So that makes your life much easier as far as label encoding is concerned. But ReLU has its own problems, right? So any non-negative data, any negative data, sorry, gets immediately squashed to 0. So for any negative data, the output will always be 0, right? So in that case, you'll have to sort of rescale or shift your data and all that nonsense. So the point I'm trying to make over here is that be aware. Whenever you're performing label encoding, be aware of what output you want to receive and what is the range of the possible output that you can achieve, and whether your data labels, the label encoding is compliant with those particular outputs. Okay. I hope everybody is with me on this and you understand what I'm trying to say. Okay. So we talked about label encoding and data encoding, if you will, right? But what if we have insufficient data? What if we have simply insufficient data? Now, why would you have insufficient data? Well, sometimes you have come up with a very unique problem that has not been explored, and there has not been any data that has been generated anywhere in the world. That's obviously a possibility today. But a more real possibility is that some processes are extremely expensive to run and therefore generate data. Because remember, the objective is to figure out mathematical equivalence of some underlying physical process, right? I'll give you an example. During my doctoral days, when I was doing my doctoral, there was a very interesting problem that came to us pertaining to the fatigue level, relating the fatigue level of astronauts as a function of how many hours they have been awake, right? So it turns out, so one way of measuring fatigue is through what we call as the KS score, right? It's a sleep score. One way of measuring the fatigue level is the KSS. Now, as you can imagine, this particular study had very, very, very few data points. I remember we only got about 10 data points. That's it. Now, somebody could ask, well, why didn't we have more? So you can imagine this study was being conducted in the International Space Station or possibly in some other lab involving real astronauts and asking them to perform some cognitive action or some function or some activity while keeping them sleep deprived for a certain number of hours. Right? So you can't really replicate some processes. Right? So there is always going to be a possibility that you might have insufficient data. Now, if you do not do anything about it, if you go ahead with insufficient or low volume data, invariably, you will have a very poorly trained model, which will not do a good enough job because data is your friend, right? Volume of data is your friend. High volume data is crucial for a good and successful machine learning deployment, right? So what can you do about it if you have such scenarios? Well, you could cheat a little bit. You could quite possibly interpolate data. You could add some synthetic data, right? So something data which is not real, but does not necessarily violate the physicality of the process, right? So let's say I have, these are my data points. So I am going to say that my process has a single feature, and it's the features are given by some y, and this is my x, right? So x is the feature, y is my output. And these are my 4 data points that I have. Right? Now, I want to be able to figure out some way of doing a good approximation of this relationship, this fit. And this is what it is. At the end of the day, this is what machine learning is all about. So using it, looking at it very trivially and very simplistically, what am I trying to do? I'm trying to compute the parameters of this curve, right? Now, I only have 4 data points. What I could do is I could take these pairs of data points and do a straight line fit and use interpolation to add more data between these 2 points. So this is what we call as linear interpolation between successive data points, right? What I could also do is do a sort of a curve fit across, let's say, 3 data points. Do a curve fit, say a 3rd order or a 4th order polynomial, and use that to perform interpolation, nonlinear interpolation between successive pairs of data points. So in other words, what I'm doing is I'm injecting more data. I'm adding more data points. Now, don't get worried, because these data points may not necessarily be possible as a physical output, but they would help you in figuring out the underlying process physicality. I hope you understand what I'm trying to say over here. So this is, I mean, obviously we're trying to cheat, right? And why do we have to cheat? Because we don't have enough data. So what we are doing is we are injecting synthetic data through, by assuming that between successive data points, there's not too high a variation in the process. So the process, for example, when I do this, if I were to do this, I am assuming that the underlying process has this kind of variation, right? I assume this, which is a reasonable assumption to make. But if my process was actually like this, right, and I had these data points, then obviously my assumption of performing the interpolation will be null and void, right? So there is a certain grain of salt. You have to do this with a certain grain of salt, right? You take it with a grain of salt. Anyway, so how do you increase your data? How do you add more data? You do this by interpolation, usually, right? Now we come to what are some of the potential problems with data, right? So problems with data, well, the most common problem with data, apart from lack of data or lack of data, is noise. Now, noise is unavoidable. It's one of those constants in life, right? How do you get rid of noise? How do you, and by the way, what is noise? What is noise? For example, you could say that outliers also are a form of noise. And you would be correct in your assertion that outliers act as noise, because noise takes away from the problem at hand, right? It takes away from the problem at hand. Now, why does noise appear? It could be due to a variety of reasons. Noise usually is multimodal in nature. It could be because of channel error, it could be channel noise, it could be transducer noise, it could be sensor noise, it could be storage error, it could be anything. It could be quantization error, it could be anything, right? It could be digitization error, anything, right? So noise is noise, right? So how do you get rid of noise? So if you have noise, and if you have noise, then how do you get rid of noise from your data set? Because remember, noise will have to be eliminated, right? I mean, that's what common sense tells us, right? We are inherently programmed to assume that noise is just bad and you need to get rid of it. So if you have to get rid of it, how do you get rid of it? Well, you usually filter out the noise, right? So if you are going to filter out the noise, keep in mind that whenever you're performing filtering, there's a high probability, or it is very likely that your data will get attenuated. Your real data will get attenuated. In other words, the magnitude of the data might go down, right? So keep in mind and make sure that you account for that before you perform any kind of filtering, right? So apart from that, certain filtering techniques can also change the length of the data, the sequence length of the data, right? For example, if you use an endpoint filter, right? So an endpoint averaging filter, right? So when you do this, you're going to certainly smooth out the curve, smooth out the data, but the resulting sequence will not have the same original sequence length, right? So keep that in mind. Always be cognizant of the fact that whenever you're performing any operation to remove noise, right, your filtered data may have slightly different characteristics, may have slightly lower amplitude, might have slightly lower, could potentially have lesser number of points, and so on and so forth, right? So keep that in mind, right? But noise is not always bad. Noise is not always bad. Noise sometimes is deliberately added to the data. And this is very pertinent when you're using somebody else's data set, right? So when you look at, for example, if you go to UCI, right, and you use their database, a lot of their database has been very painfully cleaned and labeled and digitized and, curated, right? So these are clean data sets, right? And which is good for, prototyping your learning model and all that. But if I want to deploy my learning model or my trained model in a real world application, in a real world where data is going to come in noisy, data is going to come in erratic, then one way to improve the robustness and resilience of my network is to actually add some synthetic noise or artificial noise to my clean training data, right? So if you training with noise can actually increase resilience and robustness. To understand how this makes sense, think of vaccination. What is vaccination? And then it is particularly pertinent these days. With vaccination, you're deliberately adding some noise to your immune system. What is that noise? A disruptive noise. It's those weakened viral cells, right? Virus. You introduce that into the bloodstream and you allow the antibodies to form by your own immune system, right? So you're building a more robust immune system by deliberately adding something which is a contagion, right? Similarly, when you add noise, you allow for improving the resilience and robustness of your trained model. So, well, the natural question to be asked is, well, how do you add noise? Well, noise is as simple as adding some high frequency Gaussian noise. You generate some high frequency samples and add them to your features, right? So that's not an issue. So a good assumption is to add some Gaussian noise, right? So that's usually, it tends to work fairly well and does not violate any underlying physical process, right? Okay, how are we doing on time? Okay, so we're almost at the 1 hour mark. Vishal, are you there?
Yes, sir.
We're good with time, right?
Yes, sir. We have almost 1 more hour to go.
All right. So I am not going to take too much more time. I would like to continue anyway. So anyway, guys, moving on. So what is the other potential problem that you can face? Well, what if your data has some missing samples? Well, not samples, but missing attributes. For example, again, due to a variety of reasons, your database might not be, the integrity of the data might not be very, very high. For example, some features might be missing for some samples. So what do you do then? Remember, I had mentioned that every single sample in your database must have all the same number of features. And each of those values or feature values must be reasonable and logical, in the sense that they should not be absurd values, right? And they should be present, right? So what if your features, some of the feature values are missing, right? It could be due to read-write error, it could be storage error, it could be anything, right? What do you do? Well, if the number of such errant samples, a number of such bad samples is a very, very small fraction of your overall population size or sample size, you can simply delete those samples. Delete those samples. Now, what if that is not the case? What if you are working with limited data to begin with, right? What if you're working with limited data and yet you come across samples that have some features which are missing? Well, the other conventional or the well-accepted approach in such cases is that you replace those missing attributes with some derived metric from the other available values of the same attribute. For example, if in particular, I have this human population database and some samples are missing their heights, right? So if I only have less than, if 0.1% of the samples are missing the height attribute, fine, I'll ignore those samples. I'll simply delete those samples from the database. But if I only had 100 samples to begin with, and all of those 10 samples are missing their height. I can't really afford to get rid of 10 samples. 10% of the data is quite a lot. Question? Is there anyone who has a question? All right. So, because I can't afford to eliminate 10% of my samples, what I will do is I'll take the remaining 90, and for example, I could use average of those 90 remaining heights of the 90 people, and use those values to fill in the missing 10%. Is that good? Of course. Is it ideal? Of course not. But is it very, very bad? No, absolutely not. Because it is better to assume that the remaining 10 samples have an average height value than picking up something which is completely absurd. Right? Or I could use the median value of the sample, right? The remaining value. So the point is that you could replace the missing attributes with some derived parameter or derived metric using the remaining available attributes. Okay, that's one way. I must mention that it is always a good idea to randomize the order of the data that you have before you proceed with any learning or training algorithm or training process, always. Now, the reason why this is important is because if your data has been arranged sequentially, then depending on the nature of the machine learning algorithm that you're using, it may get stuck in a local minima and not be able to get out of it because of this sequential bias. Okay? So it is always a good idea to randomize the order in which the data is presented for training. Now, most learning algorithms today, modern learning algorithms or toolboxes, they have this built in, inherently built in. The reason I mention this today is because as researchers or as somebody who's going to get into data science or machine learning, it is something that will come useful when you're trying to figure out how to improve the performance of your training model. This is one of those checkpoints that you can always go and verify. Right? Okay. Let's go back to the one more thing, and that is the variety of data, right? The variety and redundancy of data. You might recall that at the very beginning of this talk, I had mentioned that volume of data is just one aspect of the coin. The other aspect, obviously, is variety of data. How much of my data or my sample size or my population space, if you will, is in the database, right? So higher the variety or the quality of data, the better off I'm going to be, because that is going to increase the robustness of my training model or my learning machine. So it is natural to ask, well, what is an acceptable level of variety? Well, to put it in a very non-technical and non-threatening way, if you will, the database should have samples, at least one sample, or at least sufficient samples of every class of samples, every class of the population. Okay. For example, if I'm trying to figure out, going back to my machine learning example that we've been trying to use, is I am trying to identify the ethnicity of the person. So if I say ethnicity, I mean Caucasians, Pacific Asians, and so on and so forth, right? Then my database, my training database, must have sufficient samples of Caucasians and all the other ethnicities I can possibly encounter. I'm not saying that you should have, samples belonging to Martians, because you're never going to see Martians, right? At least not yet. But it is always going to be a good idea to have sufficient number of Caucasian samples, sufficient number of Asian samples, sufficient number of Pacific Islanders, sufficient number of African Americans or Africans and whatever, Hispanics, right? Because those are the ethnicities that are possible in a real world application such as CCTV or surveillance camera trying to detect the ethnicity at an airport, right? So the number of samples, there should be sufficient number of samples of every possible class of population, a class of samples that you intend to encounter in the actual practical deployment of your solution. Okay, right. The other nuance of this whole database is how do you split how much data to use for training and how much for testing? So general rule of thumb is that you always use between 70 to 75 or even up to 80% of the data, training data for training, and the remaining for testing and validation. What is important to be noted over here is that your training and test data should not have any overlap. Now, if you have that overlap, then you are risking what we call as memorization problems, right? So or you should take special care to ensure that your database has been thoroughly randomized, and from that randomized database or randomly sequenced data, you take about 70% separate or 75% separate, and the remaining for testing validation. In other words, they should be mutually exclusive. And care should also be taken if you have a lot of redundancy in your data.
Only participants.
Pardon me? Is there a question? Okay. The other thing is that you should take care that if you have too much of redundancy in the data, so that means repetition in the samples, again, you're going to contribute towards problems in training. Convergence, when you have a lot of redundancy, you will find out that your training performance is very good. Potential. Hello? Hello. Right. So redundant data samples should be eliminated. And last but not least, I want to touch on a few salient issues as far as data is concerned, and getting yourself ready and talking about performance of your training. Vishal, could you please mute this speaker? I think there is some noise in the background.
Okay, sir, I'll do that.
Okay, thank you. So data is not the end of the story, So when you take a holistic view of your array machine learning, data is not the end of the story, right? So if your model is not giving you the desired performance, right? It is not working at a desired level of testing performance. You don't have to beat yourself about it. You step back and assess. Why is the testing good? Are there too many weights? For example, if I'm using ANN, are there too many weights in the network? Is the network architecture overly complex? Is the network architecture too dense? Is the data because the number of weights, Vishal?
Yes, sir.
There's a lot of noise coming from somebody's channel. If you could.
Everyone, please mute your mic if you can. Please, I cannot see anyone's mic open right now, but please make sure your mic is on mute.
Okay, right. Thank you. Right. So if my network is not giving me sufficient testing performance, right? So it might not only necessarily be because of data. I mean, yes, it might also be simply because that my network itself, given the data that I have, my network itself is overly complex, right? So to put that in perspective, with ANNs, artificial neural networks, right? One unwritten rule, or if you will, or sort of a broad rule of thumb or heuristic rule is that the total number of weights in the network, that when I say weights, what do I mean? The weights between the input and hidden layer and output layer, right? The total number of weights should not be more than 1/10 of the total number of samples available for training. So if I have, for example, 100 samples available for training, then the total number of weights should be less than or equal to 100 by 10. Right? With anything more than this, you're increasing the complexity of the network without providing sufficient data size, right? Additional data points. So that's one way. That's one of the things that you can reassess. You could also look at whether you need to deploy a different machine learning algorithm. For example, if you're only doing classification, right? Then if you want to perform n category classification, maybe instead of using n class ANN in the output stage, you could perform n class, use a SVM and perform n class SVM through 1-to-1 or 1 through many strategy, right? SVM support vector machines are binary classifiers, but you could deploy SVMs in a 1 versus rest or 1 versus 1 configuration and achieve the same n class classification. So these are things that you need to quantitatively evaluate. Now, why do I say that? Because most of machine learning is driven by heuristics, right? There are no hard and fast rules. Most of it is based on experience, heuristics, and some cardinal rules, right? So whenever if you're getting stuck with a low performing mathematical model or machine learning model, always step back and reassess. Maybe my my data encoding was incorrect. Maybe my activation function needs to be reevaluated. Maybe my training algorithm needs a little bit of correction. Maybe I need to change the architecture of my network. Maybe I need to use a different machine learning algorithm itself, right? And so on and so forth. Right? So the reason I mention this is because you got to understand machine learning has incredible applications. Put that in perspective. Mathematically speaking, if you have a continuous function, then a simple 3-layer neural network given hello. Can you guys still hear me?
Yep, we can hear you.
I think there was a disruption in the network, a very quick, rapid disruption in the network. So where did I lose you guys? Hello?
So we were discussing the silent features of the data, and
All right, right?
Yep.
So, this, so if you think about the Fourier expansion, right? The same logic can be used to understand the expressive capability of neural networks. So, because neural networks or machine learning algorithms can be incredibly powerful and have very, very diverse applications. So do not look, if you end up with a model that is not performing to your expectations, it's not just a single point failure. The point I'm trying to make is that a low performing mathematical model has multimodal failure points or multiple failure points. And those failure points need not all be data driven. They could also be because of your algorithm. It could be because of your network architecture, because of your approach, because of a variety of reasons. So if you want to succeed, if you really want to be systematic about it, you have to take each of these aspects sequentially and examine them one by one. Why? Because there are no hard and fast rules. A lot of machine learning is driven by heuristics. All right. All right, that'll be the end of my talk today. Now I'm going to answer any questions that you might have. Okay, so I'm going to open this up for questions, Vishal. It's almost 11:30. I think giving about 20-25 minutes. Q&A.
Thank you so much, sir. I think that we are on time with this, that we already planned the session to have 30 minutes for open discussion. Okay. So I would request all the participants to please, one by one, if you have any questions, please raise your hands. And when your name is called, please ask any questions if you want, because if all of you start speaking simultaneously, okay, Kshitij Chaturvedi, you can ask question to Dr. Ashutosh over here. Sir?
Yeah.
Okay. Yeah. Hello, sir. This is Kshitij.
Hi, Kshitij. Can you turn on your camera, please? It's good to see somebody's face.
Okay, sure.
You can turn it off later. It's fine.
So actually, sir, I was following your talk over machine learning very properly. I just need to know one thing. Mm-hmm. So you have explained within ANNs, we need to follow n-10th of the rule. So is it for all of the categories of ANNs? Like either for aerospace or like if we talk about speech or software or time series predictions, all of them, this is the same rule we need to follow?
Again, so this is something, so have you read a pattern classification by Duda and Hart?
No, sir, not yet.
Okay. So this actually was, I remember reading this in that particular textbook. So I would imagine that, yes, this holds true across, irrespective of the domain of applications. So if you're using ANNs, this is a good rule to follow. So what this rule does is it prevents you from getting carried away. So, okay, why do I say this? We tend to mistakenly believe that if I simply increase the number of hidden layers or the number of hidden nodes, right, my network will become very, very powerful.
Exactly.
What most people don't realize is that the expressive capability of the network is directly dependent on not only the network architecture, but also the amount of data it has access to learn. Right? Now, let's assume for a moment that the amount of data that you have is fixed.
Okay.
Right? So the volume of the data is not going to change anymore. The only thing that you can change is your network architecture. So then, where is that optimality point? What is the good compromise? Therefore, they say, now, because the number of hidden nodes and, okay, now let me go back. When you're deciding on the architecture of your neural network, what is the one parameter that is in your control? See, the number of input nodes are fixed by the data and the number of features. Yeah? Yeah. The number of output nodes are dependent on the problem at hand. So if you're doing a one class, binary classification, n class classification, whatever, right? So the input and the output layers are sort of fixed by the problem at your hand, right? Input is fixed by the data dimensionality, the output is fixed by the objective you're trying to achieve. The only thing you can change is the hidden layer, the number of hidden layers and the number of nodes in the hidden layer. Yeah. So the moment you change the number of hidden nodes, the number of weights in your overall network change, right?
Okay. Okay.
Which changes the computation. So as a result, the good compromise is that the total number of weights in the network, your hidden layer or hidden nodes should be adjusted such that the total number of weights in the network should not be 1/10 the total number of samples available for training.
Okay, gotcha.
All right.
Okay, sir.
Okay.
And also, sir, the book you mentioned, can you mention it over the chat so as we can refer it like for the future references? The book that you just mentioned.
Yeah, very, very famous and very old book called Pattern. My all-time favorite book in machine learning.
Okay. Okay. Thank you, sir. Thank you so much.
Thank you, Kshitij. Okay, Akansh.
Yeah, hello. Thank you, sir.
Hi.
Thank you, sir, for having us such a comprehensive.
I can't see anybody. Vishal, this seems so strange.
Okay.
Akansh, can you please start your video?
Yeah, I can try it. Maybe there is some bandwidth issue. Maybe I will try it.
It's okay. Yeah,
It's
please,
okay.
go ahead.
Am I visible?
Yeah.
Yeah. So, sir, I have two questions. One was regarding a class imbalance. I was working on some project, and then I found that I was working on classification problem, and there was like one class having only 300 examples, and other was having like 1700 examples. So, can you discuss that? How can we improve on this? And if there's a case of class imbalance? And regarding that n by 10 rule, I'm not able to understand why does it work and what is the need of that.
So let me first try to answer your first question, that is class imbalance. Now, class imbalance is because of the nature of the data that you have sourced, right? So depending on Akansh, where did you get the data from? The class imbalance?
Actually, sir, I was working on a project by IIT Bombay. So I was working on their lab, and it was regarding the ID classifications.
So did the class imbalance actually create problems with performance eventually?
Yeah, sir. The thing was that we have to classify a college ID card from not a college ID card. So Aadhaar cards sometimes were classified as a college ID cards.
Okay, right. So you were were you using artificial neural networks?
Yeah, I was using deep learning models.
Okay.
Yeah.
So I am assuming that if you could reformulate the problem, for example, if you let's assume that you can't increase the number of data points, right? So if you can't increase the number of data points, and this class imbalance does exist, then you could step back and say, okay, my objective is to take a decision on whether this is a valid ID card or not. So it's a binary classification problem. In that case, you could possibly explore using SVMs rather than ANNs. Okay? Because SVMs are not necessarily as susceptible to class imbalance as much as ANNs are. Hello?
Yeah, okay, sir. But the thing is that it is very well known that CNN works better for image classification rather than SVMs.
Fair enough. So, Ravi, मैंने पूछा ना कि आपका objective क्या था? If the objective is only to evaluate whether a ID is genuine, is a college ID or not, you understand what I'm saying? If your objective is only to evaluate whether if the problem at hand is to evaluate whether a given ID is college ID or not, right? So then it becomes a binary classification problem, right? True, false, high, low, yes, no, right? Then that same data can be fed to an SVM classifier through appropriate kernel transformation, that you might actually be able to get reasonably good performance as compared to CNN. Now, you're using CNN because you want to perform this decision making in the image processing domain. Fine, okay? But you are deriving some features, right? You're computing some features from the images and you're feeding it to the CNN, right?
Yeah. Yes.
Okay. So if I'm not incorrectly assessing the problem, the point I'm trying to make is that your objective, the problem objective, could be approached using a different method. So if you absolutely positively must have to use CNN, then ask yourself, why is that? So remember I had mentioned one of the disturbing trends. This is an example of that, right? Okay, from a learning point of view, fine. But class imbalance is class imbalance, right? So if you have lesser number of samples, there's not a lot you can do about it. So you have to figure out how do you work with the limitation, not by the limitation, right? But anyway, getting back to, I hope that helps you in some way or the other. But the other problem, the point that you mentioned, was this n by 10 thing, right? Akash?
Yes.
Okay. Let's go back to this. So let's take your example. You have a data set. The data set is nothing but a collection of attributes per sample, right? So features per sample. So X number of features on the input side and some output. On the output side, you have, let's say 1, 2, 3, 4, whatever the number of, or maybe one node on the output side, because you're trying to figure out whether it is true, false, yes, no, high, low, right? So your network architecture gets fixed on the input and output side by these facts of life, that your data has these many input attributes. So the input layer has these many nodes. Your output has to take a binary decision, so it has a single node on the output side. What can you change? If you're trying to play with the network architecture to get more testing efficiency or more testing performance, what is it that you can do? The only thing you can change is altering the hidden layer architecture, right? The moment you change the hidden layer, if you add one more node on the hidden layer, then n, where n is the number of features, n weights increase on between input and hidden layer, and n weights increase on the output between input and hidden and output side layers, right? So with every change in the input layer size, the number of weights increases. Your entire process, the entire training process, learning, performing training, is nothing but computing these weights, the optimal value of these weights. Yes or no? Which means that having a higher number of weights to compute presents itself as a computational task. So if you do not have enough data, then having a higher number of weights gets defeated as a purpose. It defeats the purpose. So a lot more intelligent people than I am in the past have figured out through experience is that they say that your network architecture should be such that the total number of weights in that network, should not be more than 1/10 the number of total training samples you have. Okay?
Yes, sir. Thank you, sir.
You understand now?
Yeah, yes. Just one more question, sir. Sir, yeah, if we are classifying two classes, like for dogs and cats, and we have to make a deep learning model for that, what if I pass some another image, like for image, example, an image of human, and it is classified, maybe it would be classified as one or the another, maybe a cat, maybe a dog.
Yeah.
So, I mean, how can we overcome this problem?
It's like asking, how can I prevent somebody from destroying my work? Right?
Yeah, maybe.
But there is no hard and fast answer to this question. Think about it. If you develop an algorithm that performs classification, okay, and you put it online, and you say that this is a good learning tool to explain kids how machine learning works. And if you upload an image of an animal, it will try to figure out if it is a cat and a dog. Fine. Is there anything stopping me from going to your website and uploading a picture of myself? No.
No, sir.
Does that mean that your work is meaningless? Of course not. What it does mean is that I am the idiot. So don't worry about all that. This what the fundamental assumption whenever we have such talks is that people are serious about the work that they're trying to do. Right? So anybody who's trying to deliberately feed misinformation to your sample or your train model should not be surprised if the answer it gets or the verdict it gets are illogical. Yes or no?
Yeah.
Don't worry about it. Don't worry about it. That's not an issue. Okay. Next question.
Thank you, sir.
Okay, thank you. Okay, so sir, the next question would be from Rajesh Kumar. He has raised his hand, and Rajesh, I would like you to ask the question, please. Rajesh, can you hear us? Okay, I think he might have lost his connection. So, sir, the next question will be from Umang Singh. Umang, feel free to ask the professor anything you might.
Thank you, sir, for enlightening the beautiful talk. And sir, I am having a question that with the growing idea of IoT, we usually face the challenges related to scaling in IoT in terms of data. As we are moving towards the important aspect because technologies are getting increased and we are having a bulk of data. So, sir, you have beautifully explained regarding the data scaling. So, sir, my question was with you, how data scaling can be done using sensor networks for IoT applications?
Always remember that the scaling will always have to be post-processed, post-performed. Right? So, depending on the sensor that you're using, your sensor may not give you scaled data. That's okay.
Right. Yes.
Nothing wrong with it. Once you capture the data, then scaling again, you can perform scaling using any of those two techniques that I've mentioned. Look at the data that you're getting. If the data has a fairly strong Gaussian distribution, perform standardization. If it is non-Gaussian, non-normal distribution, you can perform min-max scaling. There are many other scaling approaches, right? But the key to take away over here is that scaling is entirely going to be done by you as a scientist. And you have to ask yourself, do I need to do scaling? Because if you're performing, let's say doing, okay, let me rephrase this. Scaling is always a good idea, okay? Always. But if you do not want to do scaling, then remember that only certain machine learning algorithms do not worry about scaling. Like for example, clustering, right? Clustering is okay.
Yes, sir.
If you don't do scaling, you're okay. But with ANNs, unless you scale the data, you're in serious trouble. So to answer your question, scaling is going to be done by you, and it will be context-aware scaling, right? So what is the context? Where are you going to deploy your data? Where are you going to deploy your trained model? The model that is going to work on the data coming in from your sensor network, it is going to be deployed somewhere, right?
Will it also be depend on the type of the data? Because if I'm taking the example of parking approaches, then we would be we need to calculate the images from the image data set. And if we are talking about the textual data, then approaches would be different. Am I right, sir?
Absolutely. Absolutely. So I will go back to my statement saying that scaling is always a good idea. How you perform the scaling is, again, like it should be context aware scaling, right? So what is the context of the?
Right, sir. Thank you so much, sir. Thank you so much.
Thank you, Umang, for I hope all of you are satisfied with the answers the professor has given over here and the talk which which was given by Dr. Ashutosh over here. Actually, I am very satisfied and I felt great, sir. That was a great talk and I was continuously in this session over here.
Okay.
And thank you so much for speaking with us, sir. And it was very insightful.
Thank you. Thank you all.
Okay, so thank you everyone for giving us your time and participating in the event. We shall meet at 3 o'clock again. The next session is from Dr. Vijay Bhaskar Semwal. He is from Maulana Azad National Institute of Technology, Bhopal. He will be, once now you are after the talk of Dr. Ashutosh Mishra, you now know what to do with the data while you are preparing yourself for machine learning. Now, so the next session will be Introduction to Machine Learning and Data Dimension. The meeting room will open at 2:30. So I suggest that you log in into the sessions few minutes before the actual time of this session. So again, this session will be of 1 hour 30 minutes or approximately that, and after the last 30 minutes will be open for questions. So I hope to see all of you at probably 2:30, 2:45. Thank you so much.